You ever look at a mathematical paper and feel like you're trying to read a secret code? Just a wall of symbols that seems to hide some powerful hidden idea. Well, today we're going to decode one of those papers together. We're going to uncover a really fascinating strategy for solving a very, very old problem.
Okay, take a look at this. This is a 10th degree polynomial equation, and it's pulled directly from our source material. I mean, it looks like an absolute monster, right? Just a string of mathematical chaos. But what if it's not chaos at all? What if it's actually a map?
Because this exact equation holds a really clever approach to a whole class of problems that were famously proven to be unsolvable by any single general formula. So the real question is, how in the world do you solve the unsolvable?
All right, here's our game plan. First, we're going to unpack the puzzle itself. Then we'll get into why this has been such a huge historical challenge. After that, we'll uncover the paper's key strategy for simplifying things, see it in action, and finally, we'll talk about why solving these ancient problems still matters so much today.
So, first things first, let's get a handle on what we're actually dealing with here. What is this giant equation really asking us to do?
At its core, this whole thing is about polynomials. And the easiest way to think about a polynomial is just as a recipe for drawing a curve. The degree, that's the highest exponent you see, like the 10 in our example, that tells you the maximum number of times that curve can bend and turn. So the higher the degree, the crazier the shape can get. So the challenge isn't just about drawing the curve. It's about finding the exact points where it crosses zero, what mathematicians call finding the roots. And that is where we hit a massive, monumental problem. For centuries, math was just this steady march of progress. Equations of degree 2? Yep, we've got the quadratic formula from high school. Degrees 3 and 4? Okay, those formulas are way, way messier, but mathematicians figured them out back in the 1500s. But then, when they got to the 5th degree, they hit a solid brick wall.
And here's the crucial point. This wasn't just a case of the formulas being too hard to find. No, in the 19th century, two brilliant mathematicians, Abel and Galois, proved it was literally mathematically impossible. There is no single one-size-fits-all formula that can solve every single polynomial of the 5th degree or higher, period.
So, if a general solution is impossible, what's this paper doing? Well, it doesn't try to break that fundamental rule. Instead, it offers a really clever method to simplify specific types of these hard equations, ones where the solutions have a kind of hidden pattern that this method can sniff out. It transforms them into something we can solve.
The core strategy is, well, it's pretty fascinating. It involves taking a set of numbers and using them to calculate a brand new set of coefficients, those little s values we saw in that first scary equation. And here's the magic trick. For these special polynomials, this process is specifically designed to make a bunch of those new numbers just become zero.
And this slide just says it all, doesn't it? The whole process is designed to take that monster on the left and, if the conditions are just right, make most of its parts vanish. What's left behind can be turned into a basic quadratic equation, something we can all solve. It's a strategy of transformation, not brute force. Pretty cool.
All right, let's see how this thing actually works. We're going to use an example straight from the paper, and this is where the theory becomes a real practical tool.
So here we see the results of the calculation. The paper feeds in a specific set of numbers. It applies its special method, and it calculates those 10 s coefficients from S0 all the way to S9. And what comes out the other side is, well, it's remarkable.
This right here is the big reveal. It's the aha moment. The calculation causes this cascade of zeros. Seven of the 9 key coefficients in the middle of the equation, they just, poof, they completely vanish.
And because all those terms disappear, our huge 10-term polynomial just collapses into this beautifully simple form. All that's left is the x to the 10th term, the x to the 5th term, and a constant number. It's the same exact problem, just with all the complexity stripped away, revealing its simple core.
And from here, the final move is just incredibly elegant. If you make a simple substitution, let's just say y is equal to x to the 5th, the equation instantly becomes a basic quadratic. You solve for y using the formula we all learned in high school, and that gives you the answers for x to the 5th. The impossible problem has been transformed into a totally solvable one.
Okay, so this is a very clever math trick. But let's be real, why should we care about solving these centuries-old puzzles? Does this stuff have any bearing on the real world?
And the answer is a huge, resounding yes.
Yeah, these aren't just abstract problems for a classroom. High-degree polynomials are the secret backbone of tons of modern technologies. They're used in cryptography to keep our digital information safe, in physics to model complex systems like planetary orbits, in engineering to design everything from bridges to aircraft wings, and in computer graphics to render all those smooth, realistic curves you see in movies and video games.
And this gets to a much deeper truth about science, doesn't it? The purely intellectual quest to solve a puzzle, a challenge that might seem completely abstract, often ends up creating the fundamental tools that engineers and scientists will use to build the future.
So I think the biggest takeaway here is the power of a new perspective. This problem wasn't solved by breaking the rules, but by finding a clever way to transform the problem itself. And it really makes you wonder, right? How many of our own challenges today, the ones that seem impossible, are just waiting for someone, somewhere, to find a different angle?